Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about space-based solar power. I covered this topic 4 years ago. Things have changed now. So why exactly we are thinking about this weird idea? Well, reality is the hard truth, renewable energy is intermittent, meaning you can't count on it. This is a very good graph right now because of the wind energy's prevalence in our grid. There has a lot of money spent into predicting it. Now, this is right now we are thankfully at least close enough where we can predict, but this should give you a rough idea. This is like over few days, but here's the deal. At the worst day, you can reach almost 0 megawatt, and at peak days, you can reach almost 600 megawatt. That is too unstable. Like from a large, grid point of view, this is just not acceptable. You want it would be much better even if it's like 150, but reliable. That would be much better for the grid. But having this like hululululu is not acceptable. And this is another graph. It's a bit, older in terms of data, but it does illustrate a point quite well. There are year data, meaning from 2006 to 2007, from 7 to 2008, and they are two different color. But here's the deal: in the same month, they are different. Basically, in October, you are getting more or less the same, but in February, one year you're getting boatload of more power, and in next year you are not getting enough. So it's not even seasonal; it's like good luck. So that creates a very serious issue where you cannot count on it with your eyes closed. This is another example from Germany from 2012 to 2020, and as in, like, you can pay attention to the coal is creating a very big role, and coal has went down, but it never went down too much. Why? It's not reliable. Solar is not reliable. You just hope that solar is like production is high and all that jazz, but if not, then you have to use coal. That's the serious issue. So what can we do? Well, assumption right now is that space is a free from weather place, meaning you do not have to worry about clouds, you do not have to worry about weather, you do not have to worry about wind. It will work there. Sun is there 24 into 7 into 365. So meaning you do not have to worry your power source going down. That is a very critical factor. Now you may think geostationary satellite remains in the sunlight. Well, technically yes, for majority of the time, but sometimes during like equinoxes, they reach a point where they go through the shadow. I do not know the exact precise timing, but apparently it's supposed to go down through Earth's shadow for 70 minutes, and that creates a very huge drain on the batteries, and that's the limiting factor of geostationary satellite, meaning the battery will wear down. Of course, it's a battery, so you can't expect a geostationary satellite to last for very long because that battery is the weak limit. But if you tilt the angle from geostationary, benefit of geostationary is exactly the same, meaning from you looking towards the satellite is exactly, it's not moving even a little bit. But if you go away from geostationary to geosynchronous, meaning you just tilt that orbit, you can achieve a point where it will be free from Earth's shadow no matter what, meaning 24 into 7 into 365, meaning there will not even be a single 70-minute down period. It will be constantly in the sunlight. And it also has very good advantage for the equipment, because if you are in constant temperature, meaning sunlight is hitting on you and it's exactly the same. Let's say everything in your spacecraft reached 70 degrees Celsius and that's it, it's not going down. That's awesome. Like, that's much easier to design for compared to something that goes into, let's say, even 50 degrees Celsius, then it goes to night 30 degrees Celsius. That 50-30 is really brutal on things. Expansion, contraction. If you are like heat it up, it's 70 degrees Celsius, it's gonna stay at 70 degrees Celsius without any issue. That's awesome. Engineers are like, shut up and take my money. It's super easy channels to do. But that's the whole thing. That's why you also want it to be in sunlight 24 into 7. Once you reach the equilibrium level where the energy temperatures have equalized, it will not change, meaning it can work for decades. Rather than ISS where it's like, things are starting to crack. You do not want expansion and contraction. Hot temperature is not an issue. Changing temperature is an issue. So that's the idea behind it. So what we are talking about? We are talking about huge thing, meaning it's big. How big we are talking about? We are talking about something that is measured in multiple square kilometer. You're not talking about a small boy, you're talking some big boy. So this is one thing. Now NASA did some rough mathematics and they were trying to do this in 1970 because of the oil embargo, and they had too much hope with space shuttle. So they were genuinely serious, and I'll explain why in the future. They were genuinely serious about this. This was their early estimate. So they started out with the idea of 2 gigawatt panel size, meaning 2 gigawatt power plant. Now, is 2 gigawatt a lot? Not really. I recently been to a dam that was 1.2 gigawatt. China's largest dam is around 12 gigawatt. So not too much, but again, 2 gigawatt is still significant amount of energy. And you're not supposed to have only one of it. You're supposed to have multiple of this. So 2 gigawatt satellite. Now, what does the mathematics say? Mathematics says it will have to use microwave for energy transmission. The transmitter side of things will be 1.5 kilometer. This is NASA. They did the math on this. 1.5 kilometer transmitter. Now you're like, okay, big, but not that big. 6 kilometer in terms of receiver. Now that's one thing you have to understand. The engineer talked about it very specifically. That 6 kilometer area sounds a huge area. Here's the deal. Many solar farm, basically India's world's largest solar farm, already is larger than this. There are many solar farms, secondary, tertiary, fourth ranking, fifth ranking. They exceed the surface area, so that's not an issue. We have that area, and like what Japan is trying to do is directly cover the ocean with rectangles, which is kind of simple device. It can be done. So that's not an issue. So do not get panicked by it. And that it does work 24/7. So it kind of makes sense. However, the weight, boy, it's supposed to be around 80,000 ton, and it has to be built in orbit, and that's another issue. Every time you talk about rockets, generally rocket companies always will sell you the capacity to low earth orbit, meaning this is Falcon 9, how much ton it can take? 22 ton. Where? Low earth orbit. They will not talk about geostationary, because geostationary, it can go down drastically. It can go down from 22 to 5 tons. So that is one of those things you have to understand. And when we are talking about this sort of geostationary system, you are talking about at least 35,000 kilometers, meaning it's going to take huge amount of power. And even the rocket that are like, let's say 60 ton to low earth orbit, it may go down to 8 tons to geosynchronous orbit. So you may need 8,000 launch to complete this, and that's assuming 100% efficiency, which physics does not allow, and Murphy's laws is really don't allow. So to build something this sort of thing, we have to have a huge ass rocket, be lot of launches, meaning our launch cadence. That's why NASA kind of abandoned this project. Their assumption was space shuttle will reach a point where it will be like, a few launches per month. Now they reached a point where there was like, barely doing 2 launches per year. That was just not enough cadence to do anything. And space shuttle was supposed to carry 23 ton. So at that time they had the idea that they can build it in low Earth orbit, push it the big segments into geostationary. Then like, step by step they could build it. But after realization of that space shuttle is just not capable enough, and oil embargo ran away. So it's like, that's not an issue. So we are talking about something huge here. It's not something small. So how will this puppy work? This puppy will use mirrors to remove infrared. I like, wait a minute, how the heck mirror can remove infrared? Well, you have a radiation source, meaning sun is giving out GG amounts of radiation. It has almost everything. Now, if you put a mirror here, now depending on the elemental coating that you are choosing for that, if you want to reflect infrared, you will use gold. If you want to use optical spectrum, you will use aluminum or silver or some alloy of those things to achieve perfect reflection only in that select spectrum. So if you do not have gold, that means sun is giving light, here's deals, it's going there and it's passing it through, or it's heating up the panel. That's all the only thing is going to happen. So if you have gamma rays, x-rays, they will pass through. If you have infrared, it will heat this puppy up, but it will not reflect. What will be reflected? Only the basically optical side of things. So that way, flat out, because our sun is ludicrously bright in infrared spectrum, that majority energy will be removed. So if you do not do that, you have to cool your solar panel ludicrously, meaning your solar panels, even if it's like, let's say 2 gigawatt, you may have to remove waste heat of as much as 6 gigawatts. So that's a serious requirement. Like, you want to make sure your panels are only receiving things that they can digest. Now that's mirror, and that's why if you ever pay attention to any concept created by NASA for Mars, they always have light pipe, basically periscope kind of equipment for providing lights, unless you're talking about airlocks. That has to be done in that way. Otherwise, you will give basically light a direct path into your habitat. So mirrors will remove infrared. That's awesome. It will focus sunlight into multi-junction solar cell. Now, why multi-junction? Normal basic bitch solar panels, they are generally very good efficiency, and they are very cost effective. So they can easily achieve from 20 to 25% in lab environment. In real world, 15 to 25%. 25% is like, it's really bright, but it's really cold. Then only they achieve that. But that's limited. That's very low. But when you're talking multi-junction system, where you have multiple different elements creating different solar cells stacked on top of each other, then you can achieve much higher efficiency. Right now, the lab efficiency is at around 45%. That's high efficiency. Consequence, it does require enough intensity, because you have to pump those photons into it. Otherwise, it will not work that well. And you can pay attention to that gray line is basically its energy, solar energy spectrum that we are receiving on Earth, and colored part is just how much is able to absorb. So imagine it this way: this is 2 gigawatts solar array. It's absorbing, let's say, 40% of it. That means 60% has to be taken care as waste heat. So that's why removing IR is compulsory. If you did not, it will heat up even more ludicrous. So how do you design this? Well, that's up to you. There are some designs, like this is designed from NASA. It apparently is designed such a way that no matter, like this does not require any mechanical parts moving too much. Basically, you do not want moving parts. Moving parts are a headache to deal with. That it is designed in such a way that no matter where the sun is in this orbital period, the light will be always pointing down towards the panel array. So that means it will never go into the shadow, and the panel will work 24/7. That's awesome. Consequence, it may be much huger compared to other systems. Other systems are like how ISS is, where you just have a flat panel and you're rotating it. Now you might be thinking, oh, isn't that simpler? Actually, no, simply because it does require you to have a two-part system, meaning you have to have a dish that is pointed in a fixed location that has to act as an anchor, and then you have to rotate solar farm. Now think of it this way, rotating something like this, it may require a lot of gyroscope, may require thrusters to make sure the gyroscope do not get saturated. So it's not as easy as you may think, just to twist it around. So that's why some people are seriously thinking of making a static object. Once you stabilize it, once you have correcting thrusters, it's done. This will require constant love, but it would be cheaper to build. So that's the design aspect of it. And then you're gonna create the basically use the electricity to make microwave. Microwave will be fed to earth. It will not look like this, it will be invisible, but for creative purposes they made it into a pink laser beam. So that's the working aspect of it. So what's the reality? That's the hula la idea about it. What's the reality? China is claiming some big things that they are going to test it by 2026, and their target is, again, early targets are very low earth orbit kind of target. They are targeting around 600 kilometers and only few kilowatts to few megawatts, like something small, something achievable, something can be launched in one satellite. That's their target, and they want to do big things by 2030. Let's see. Then UK research is already pouring boatload of money into the R&D part of it. Is it viable? Is it doable? And their paper is out, and somehow that paper is suggesting that it will be cheaper than anything else. I do understand the solar does not work very well in Britain, because again, India, I'm like closer to sun, so it's like equator wise, so we are like familiar with sun. You put solar panel, it works. In Britain, good luck finding sun. So I do get that point. It's like why they are saying it might be cheaper. And USA literally did a serious amount of research in 1970, and this is a physical prototype they built. So basically they were using a giant radio dish to reflect microwave, this giant radio dish, and they're transmitting it to a rectangle that will physically receive the energy, and they're gonna glow up some bulbs, like these bulbs, halogen. You can see those bulbs in daylight. That means like some serious amount of energy was transmitted. But again, they actually did the mathematics, they actually did a build prototypes, they actually went to some serious effort and serious length to figure out like this is exactly how this will work. So they have some serious evidence, as in like from a practical prototype point of view. And NASA is taking a closer look at this again. So they went from, it's like it was something that we thought in 1970 to let's open those files again, like some serious amount. And Japan is also taking it seriously. That's their aim. That's why you can say Japan, and they have like 2 receiving stations. These receiving station will convert, like they will be on the sea, so even if they have to make even larger, let's say instead of 6 kilometer, it has to be even larger, because microwave antenna is rather like a chicken mesh. So if you can make it out of stainless steel and like good plastic support, it's gonna last even in the sea for, well, decades. So that's not a very big issue. So that's the reality behind it. That's only one country has even attempted to physically try to transmit megawatts of power using microwave. Other countries have, like China is claiming they have built it, and there is a site that they have started to build the rectangle, meaning the receiver part of it. But let's see. So that's the reality of it. Right now, there is nothing physical, concrete that I can show you. But what we can expect in the future? Well, we are in a bit of a jam, so to say. We are running out of time and we are running out of money. And these two things are non-refundable, meaning once you waste time, it's not coming back. Once you waste money, you're not going to get that money back. For example, India's Mumbai government wasted a boatload of money in making Hyperloop. But Hyperloop was a scam. So they took a boatload of money from Treasury, they burnt the money, and now they're like, okay, we wanted point A to connect it to point B, but Hyperloop was a scam. So they threw it away. Okay, here's deal. Do you build, even just to build a normal metro system to like long distance metro system or express railway? No, we can't, run out of money. So that's the problem. You cannot just throw away money and time and expect everything to be like, let's try again. We are running seriously short on those two things. Now, that being said, I'm genuinely surprised that every Tom, Dick and Harry is like, including like 4 countries, they're pouring serious money into this. It's like you do realize, all 4 of you, that there is only one goddamn rocket that is even close to achieving what they are expecting. It's like there is only one company at this point in time. There is only one company that has a reusable rocket, and that again, they started with bold claim as like 150 ton to low Earth orbit, which means some serious amount of tonnage into geostationary. Then it went down to like 100. Then it went down to 80. Right now, I'm calling calling it 50. Again, be mindful, it can be done with 50 because again, NASA's the whole plan was with 20 tons. So if they can achieve 50 ton, good enough. And it will be reusable. Now, will it be reusable on day one? Hell no. It's going to go boom multiple times. I guarantee it. It's going to happen. Over time, this will be Mark 1. They will be do Mark 2, Mark 3. Like Falcon 9 Block 5, that it's, it's a workhorse now. It wasn't so. Like you can just type, SpaceX blowing up, a lot of Falcon 9s blowing up. It has to be done that way. Same will happen with this. And right now, entirety of planet has only one company that has a reusable rocket. Only one company that's even planning to make something large. Now, apparently, there is a rumor that China is trying to build something that is as huge as Saturn V and reusable. But let's see. It's rumors. It's just speculation at that point in time. Again, they have to do that, otherwise this sort of ambition is pointless. And that's the hilarious part with the UK. It's like, dude, who is the launch provider that's gonna ship hundreds of tons? That's the biggest limit. That's why, like, when Elon Musk goes against this, I kind of understand his point of view, simply because he knows how rockets work. It's like, how the heck you're gonna ship 80,000 ton? It's like we are pooping ourselves in, like, 600 ton ISS. How the heck you are genuinely expecting somebody who's like, we gotta send 800 tons? It's like 8,000 ton. 80,000 ton. Yeah, not happening. So that's a serious limitation. And be mindful to practically do it and not set the planet on fire just from rocket exhaust. You have to make sure that rocket is much larger than this. Like this 50 ton has to be Mark 1, and then they have to have 100 tons. Now, if they can reach 100 ton to low Earth orbit while being reusable, then we are seriously done. At that point, it's like something we can just, just do. Some elbow grease we can do. It would be like equivalent to large dam projects. So that can be done. But right now, there is only one rocket, and the second company that is even close to building a physical rocket that will be reusable, that's Rocket Lab's neutron rocket. That's also behind schedule, and that's much smaller. So that's the reality. It's like, let the space industry show you. It's like, dude, you need that chariot to space. There is only one chariot, and that's also under construction. So and that's one very big hurdle. Another aspect that pisses me off is, like, we have not exhausted all the solar resources on this planet. Like, this is India's largest solar farm that is around 2.5 gigawatt. Here's, did India run out of space? Even with India's ludicrously large population, we still have uninhabited place, like as in like raw deserts, where we can cover the whole place up. Not even a single person would be displaced because of it. And we will have gigawatts and gigawatts and some more gigawatts of energy. On top of that, that's just one place I'm talking about. Like, there are other secondary uses architecture. For example, canals. India has ludicrously large, canal network. Now, here's the deal. If you cover those canal network, you will have hundreds of square kilometer of area, which is already bought by the government, already in use. And if you cover those up, you will reduce water evaporation, you will keep the solar panel cool, and you will get electricity. And how about floating solar panels behind dam reservoirs? Those are also in multiple square kilometers, meaning they could be like 10 square kilometer or 5 square kilometer. They have a lot of power that we have not. I'm not talking about touching farmable land. I'm not talking about touching a land that is like in use. I'm talking about land or surface area that is not even touched by anyone. In those sort of scenario, we can do so much. And then at that point in time, only issue would be how do you store the energy, which we have other options like cryogenic air energy storage system that will take care of that system. But we have not reached a point where, oh, we have covered every square inch of coverable land with solar panel. That's like, we don't have enough. That's not the case. And solar is the only technology that is proven mathematically that even if we cover only 20% of surface area, we will have more than enough energy. What does 20% mean? Simply means cover up every rooftop that can be covered, cover up parking slots, cover up large warehouses, school buildings, basically large flat objects. And those places are already in use, so that's not an issue. It's like land is taken care of, you just use it. You do not have to touch the farming land. So that's why it generally pisses me off. It's like, dude, let's take care of this part. How about instead of your imaginary 2 gigawatt, how about we just make this, you may be like 2 gigawatt 24/7. Awesome. 2 gigawatt only for 6 hours. Here's the deal. What if you make 3 or 4 of this? And again, it's real, it's here, it's profitable. Let's just amplify this puppy. So this is one thing that bothers me. And the another scary aspect of it is, like, did all this country lost faith in fusion? Like fusion, every country like China, USA, UK, Japan, they are serious investors in fusion technology. What happened that in last 2-3 years they are starting to think about space solar? Because again, if we have fusion, fusion solves everything. Like fusion creates so much energy that we can suck carbon dioxide from the atmosphere, make it into hydrocarbon, and make it into crude oil, and then bury it in the ground and like pretend like it never happened. That's how much power fusion has. That why the heck every company is like, including China has like sun reactor. It's like, what the hell happened? I'm genuinely sure somebody, like some engineer, actually sat down, some top officials, say like, bro, here's the deal. the break-even factor that people are talking is like, we have achieved break-even, which is like, 1 versus 1.6, meaning we put 1 megawatt, we got 1.6 megawatt out of it. Here's deal. That's thermal energy, meaning you're not going to convert it into 100% efficiency. You need at least 200 or 300x. And every time somebody is building a reactor, be it MIT, be it National Ignition Facility, everyone is building, it's like, it just does not work. Why? We don't know. We simply don't know. So I think somebody's had all the top officers, because if NASA is seriously looking into this, that means they have lost complete faith in fusion. Complete faith in fusion is gone. It's like, no bro, I don't think fusion is gonna happen anytime soon. Otherwise nobody will look seriously into this. Like, you still have to spend hundreds of millions of dollars in order just to do the paperwork for this. So, and they are doing it. So it's like, I think fusion is not gonna happen anytime soon as in like next 50 years. Again, that's my scary prediction. Let's see what happens in the future. So this was my presentation on space-based solar power. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you are free. And as always, thanks for watching.